Let's move on now to closed OTEK systems. So one way to avoid turbine issues in OTEK systems is to use a binary system with a working fluid other than water. This is actually the type of system that was used in a YouTube video that I referenced you guys to the research facility in Hawaii. More specifically, it's called an Anderson cycle. And these systems usually work with working fluids such as ammonia and propane. Here's a diagram of the system itself. So you have your hot thermal reservoir source is the warm water from the surface, and then the cold reservoir would be the cool water at the ocean depths. So you have here in a boiler a heat exchanger for exchanging heat between the warm surface water and the working fluid. So this is actually like a Rankine cycle. So you have a boiler. The working fluid comes out as a superheated vapor. As a vapor, it goes into a turbine, drives the turbine, comes out of the turbine as some saturated vapor, saturated mixture. It goes into the condenser. The working fluid exchanges heat with cool water in the heat exchanger, comes out as a saturated liquid, goes into a pump to go back up to the boiler or the heat exchanger's pressure. So again, it's a closed loop where the heat engine has its four cycles: the pump, the boiler, the turbine, and the condenser. And then the heat exchanger on the boiler side exchanges heat with water coming from the warm surface temperature, and then the condenser exchanges heat with ocean water from that comes from a deep depth that makes it cold. This is an Anderson cycle. So let's go ahead and look at the example problem from the book. Example problem reads that a closed cycle OTEK system uses propane as a working fluid. So the warm surface water enters and leaves the evaporator at 28 and 25 degrees Celsius respectively. And then the cold water enters the condenser at 5C and leaves at 8C. The propane evaporating temperature is 22 degrees Celsius and the condensing temperature is 11. The plant output is 125 kilowatts. Now, just as a note, the book actually has this as megawatts, but the numbers don't make sense when it's in that high of a power output. So we're going to look at this case in terms of 125 kilowatts. And the turbine efficiency is 90%. They also give you the heat transfer coefficient in the condenser and the evaporator. So it's asking you to find the propane flow rate, the evaporator and condenser surface areas. We're actually not going to do that part. The warm and cold water mass flow rates, and then the overall efficiency. We're also not going to do that part. I just want to look at the flow rates to give you an idea of the type of flow rates this system has. Also, as some information, it gives you some saturation properties for propane. So as you can see, it gives it to you for 11 degrees Celsius and 22 degrees Celsius, along with the saturation pressures, and then all of the enthalpy of saturated fluid, the enthalpy of saturated gas, the enthalpy of vaporization, and the same thing for entropy. So looking at this, it's telling us that the propane evaporating temperature is 22 degrees Celsius. So let's assume that here at state 1, we're going into the turbine as a saturated vapor, right? So again, we're going to, based on the problem statement, we're going to assume 22 degrees Celsius, saturated vapor going into the turbine. Again, that would give us an enthalpy of 918.2 kilojoules per kilogram, according to our saturation chart here, where the enthalpy of saturated gas at 22 degrees is 918.2 kilojoules per kilogram. Now, since the turbine efficiency is at 90%, we're going to go ahead and try to find what the actual work is, but in order to do that, we'll need to find the isotropic work. So we'll go ahead and we'll get the entropy of the saturated gas as well, which is 5.621 kilojoules per kilogram Kelvin. So that's the state of the propane going into the turbine. So let's look at the isentropic case coming out. Coming out of the turbine, we're at 11 degrees Celsius, and the entropy coming out has to equal the entropy going in. So that would give me an entropy of 5.621 kilojoules per kilogram Kelvin. So with that, I know that it's coming out at 11 degrees Celsius because 11 degrees Celsius is the operating temperature of the condenser. So that means it should be a saturated state coming out of the turbine going into the condenser. So if that's the case, what I'm going to do is, knowing that my entropy is 5.621, I'm going to go ahead and calculate my quality so that I can actually get what the isentropic enthalpy is, right? So again, the saturated fluid enthalpy or entropy at 11 degrees should be 1.273, and sorry, not 1.273, excuse me, 4.359, and 1.273 would be the entropy of vaporization, or the entropy of the saturated gas minus the entropy of the saturated fluid. So in that case, I would get saturated fluid 4.359 plus X times the entropy of vaporization. In that case, I could calculate that the quality is about 99%, so it's a high quality steam. And then what I can do is I can calculate my enthalpy now, knowing what the enthalpy of the fluid plus XFG. So if I go back and I look at 11 degrees Celsius, I know this is my enthalpy of the fluid, this is my enthalpy of vaporization. So knowing that, I can take the enthalpy of the fluid, 546.2, plus the quality times the enthalpy of vaporization, 361.7. That will give me an isentropic enthalpy of 904.5 kilojoules per kilogram. So that means that my isentropic work would be the enthalpy in minus the enthalpy out if the process were isentropic. That would give me 13.7 kilojoules per kilogram. And knowing that my actual work would just be the efficiency times that. So my efficiency is 0.9. So I get that my actual work is 12.31 kilojoules per kilogram. So knowing that, I can go ahead and calculate my mass flow rate of So if I get that the work power coming out of this system is 125 kilowatts, that has to equal mass flow rate times my actual work, right, which is 12.31. I can get that my mass flow rate of propane in that case has to be 10.15 kilograms per second. So that is the mass flow rate of propane. Now, let's go ahead and let's say, okay, now that I have my mass flow rate of propane, what does that mean for the mass flow rate of warm water needed and the mass flow rate of cool water needed? Now that's a pretty direct calculation. Basically, what you have to do is if you take the boundary around the heat exchangers, right, the condenser and the boiler, you would just do a first law analysis, right? So if you do a first law analysis on the heat exchanger, the only energy exchange is energy by mass. So if you were to actually go and do that, I'm not going to go through the whole thing because you guys should know how to do first law analyses by now. But if you do a first law analysis on the evaporator, you'd basically get that the mass flow rate of the propane times the enthalpy in minus the enthalpy out has to equal the mass flow rate of the warm water times the enthalpy out minus the enthalpy in. So if you were to do that, you would find that the mass flow rate of warm water would be about 302 kilograms per second, right? Again, that's knowing the enthalpies for both the propane side and the water side and the mass flow rate of the propane. If you were to repeat that for the cold water, you would get about a similar number. I'm not going to go through the calculation because you should be able to do that at this point, but you can just see that for the propane, it's a small mass flow rate. It's only, well, not small, but I mean, it's 10 kilograms per second. You have 30 times that mass flow rate when it comes to warm water. So it just kind of shows you a little bit about how these systems work. Now, what are some other system outputs that you could expect aside from producing power? Well, here's some things that I've highlighted. You can expect, for example, desalinated water, right? The condensation of the steam, as is proposed in the hybrid OTEK systems, could provide potable water. Also, there could be nutrients for mariculture applications, right? The cold water stream for an OTEK system contains abundant nutrients and is relatively free of pathogens, so that can be used in commercial mariculture applications. Also, air conditioning for buildings and moderate temperature refrigeration, right? So you got the cold water stream can be used in conjunction with heat exchangers to provide conditioned air for cooling or chilled water for moderate temperature refrigeration applications. And then also mineral extraction. Since OTEK systems have high mass flow rates, the extraction of minerals dissolved in the ocean water has been also proposed as an additional application. Now, as far as assessment is concerned, except for a few pilot plants, no commercial OTEK facility has been built and operated. So to date, the biggest success has been a pilot plant in Hawaii that operated from 93 to 98, called the Vega, as quoted in Vega 2002. So the facility produced a net power of about 103 kilowatts and with about 255 kilowatts of gross power extracted. So the warm surface water in that case was 26 degrees Celsius and the cold water was at 6 degrees Celsius. Vega also provides a contemporary assessment of OTEK and makes several suggestions for future developments. Here's an example of a proposed 5 megawatt OTEK ship plant. So again, you have cold water intake, mixed water discharge, warm water inlets, and all the components that you need in order to make this thing work. Again, this is just a proposed diagram. It hasn't actually, as far as I can tell, as far as I know, has been implemented at this time. So, well, that about ends the OTEK side of ocean energy. In the next video, we'll move on to tidal and wave power.